bright violet line occurs at 435.8 nanometers in the emission spectrum of mercury vapor. What amount of energy in joules must be released by an electron in a mercury atom to produce a photon of this light? Before we can even really address this question, we need to figure out what we're given. We start with 435.8 nanometers, and they want us to find the amount of energy in joules needed to produce a photon of this light. Now we can answer this question using two equations. The first is V, frequency, equals E photon over H. E photon is what we really want to find. The other equation is C equals V times our wavelength. C equals 3 times 10 to the power of 8 meters per second. We don't have meters, we have nanometers. So before we can make any use of this equation, we need to convert our nanometers into meters. And we do that using this conversion factor. If we start with 435.8 nanometers, and we have 1 meter for every 1 times 10 to the power of 9 nanometers, our nanometers cancel, and we wind up with 4.358 times 10 to the power of negative 7 meters. Our wavelength is in meters, the speed of light is in meters per second. We can now make use of this equation. The speed of light equals 3 times 10 to the power of 8 meters per second, and that equals our wavelength, which is 4.358 times 10 to the power of negative 7 meters, times our frequency. In order to get our frequency alone, we can rearrange this equation. We can divide the speed of light by our wavelength, and that will give us our frequency. If we divide 3 times 10 to the power of 8, I can rewrite that a bit better. 3 times 10 to the power of 8 meters per second divided by 4.358 times 10 to the power of negative 7 meters, we will get a frequency of 6.88 times 10 to the power of 14 reciprocal seconds. And that equals our frequency. If we look back up here, we have the equation frequency equals E photon over H. So our frequency, 6.88 times 10 to the power of 14 reciprocal seconds, equals E photon, what we're trying to find, over Planck's constant, H. And that is 6.626 times 10 to the power of negative 34 joules times seconds. Now we can rearrange this. So that we get 6.626 times 10 to the power of negative 4 joules times seconds times 6.88 times 10 to the power of 14 reciprocal seconds equals E photon. Our seconds cancel, and if we multiply that through, we find that E photon equals 4.56 times 10 to the power of negative 19 joules. That equals E photon. Now let's look back at the original problem. From our wavelength, we were asked to find the energy in joules needed to produce a photon of light. If we look at our ending units, we have joules equals E photon. We've solved our problem.